Imagine a world where artificial intelligence solves humanity's greatest challenges. Now meet the man who's making it a reality. Pushing the boundaries of AI to decoding the secrets of life with AlphaFold, Hassabis isn't just imagining the future, he's engineering it one breakthrough at a time. His unique perspective, blending game design, neuroscience, and machine learning, has shaped every groundbreaking product he's created. In the next few minutes, you'll learn what is AlphaFold and what makes it worthy of a Nobel Prize, and how did a game-loving kid become the mastermind behind some of AI's biggest breakthroughs. Let's dive into the brilliant mind of Demis Hassabis. Sir Demis Hassabis, co-founder and CEO of Google DeepMind, and Dr. John Jumper, director at Google DeepMind, shared the Nobel Prize in Chemistry. Their achievement? AlphaFold, a revolutionary AI that cracked one of biology's greatest mysteries, predicting the 3D structure of proteins from just their amino acid sequences. And they weren't alone. David Baker also took home the prize of the pioneering work in computational protein design. But why does the protein folding problem matter so much? Why was solving it considered Nobel-worthy? And what role did AI play in this breakthrough? To understand that, we need to get one thing straight. Proteins are the core players in the story of life itself. Think about it. Proteins do everything. They help digest your food, enable muscles to move, transport oxygen through your blood, and even attack harmful invaders like viruses and bacteria. Your hormones, made of proteins. Your hair, yep, that's protein too. But why are proteins so critical? It's their versatility. Proteins can take on countless shapes and roles, far beyond what other biomolecules like fats or sugars can do. And this versatility all comes down to how proteins are built. Imagine a protein as a string of building blocks. These blocks are called amino acids. There are 20 types of amino acids, and each protein is like a unique recipe made from these ingredients. But here's the catch. Proteins don't stay in a straight line. They fold into complex three-dimensional shapes, and that's where things get interesting. A protein shape directly determines its function. For example, antibody proteins fold into precise shapes to latch onto viruses, like a key fitting into a lock. Understanding how proteins fold means understanding how life itself works. But here's the mind-bending challenge. Each protein can fold into an almost infinite number of shapes. According to Levinthal's paradox, any given protein could theoretically adopt around 10 to the power of 300 different configurations. Things into perspective, it would take longer than the age of the universe for a protein to try out every possible shape. Yet somehow, in the blink of an eye, a protein folds into just the right shape to do its job. This is why the protein folding problem has been a holy grail for biologists for decades. It's ludicrously difficult but absolutely essential. And that's where AlphaFold comes in. AlphaFold uses the power of artificial intelligence to predict the precise 3D structure of proteins from their amino acid sequence. In other words, it cracked the code of how life's building blocks take shape. And that's why Hassabis, Jumper, and their team's breakthrough didn't just win them a Nobel Prize, it's changing how we understand biology itself.
Until AlphaFold came along, this is done experimentally, right? Very painstakingly. So the rule of thumb is, and you have to crystallize the protein, which is really difficult. Some proteins can't be crystallized, like membrane proteins. And then you have to use very expensive electron microscopes or X-ray crystallography machines. Really painstaking work to get the 3D structure and visualize the 3D structure. So the rule of thumb in experimental biology is that it takes one PhD student, their entire PhD, to do one protein. And with AlphaFold 2, we're able to predict the 3D structure in a matter of seconds. And so we were, over Christmas, we did the whole human proteome, or every protein in the human body, all 20,000 proteins. So the human proteome is like the equivalent of the human genome, but on protein space, and sort of revolutionize really what structural biologists can do, because now they don't have to worry about these painstaking experimentals. Should they put all of that effort in or not? They can almost just look up the structure of their proteins like a Google search.
Here's a high-level introduction to the architecture of the groundbreaking AlphaFold 2. The explanation of AlphaFold's architecture is divided into three main sections. Input processing. When an input sequence of amino acids is provided, AlphaFold compares it to protein sequence databases to find similar sequences and generate a multiple sequence alignment (MSA) representation. It also searches for templates of similar sequences with known structures to create an initial pair representation, which captures the relationship between residue pairs within the target protein. EvoFormer. The unique neural network has two interconnected towers, one for the MSA representation and the other for pair representations. The MSA representation analyzes relationships between residues row-wise and column-wise, while the pair representation refines relationship between triangulating each pair's proximity. These representations communicate, iterating through calculations 48 times to produce refined MSA and pair models. Structure module. It takes the refined models and generates an initial guess of the 3D protein structure, adjusting based on physical and chemical constraints like atomic bonds and angles. The refined models go through the eFormer and structure module processes for 4 cycles to predict the final 3D atomic coordinates of the protein. Before Hassabis was decoding the secret of life with AlphaFold or building AI that beat world champions at Go, he was a game lover. And that passion wasn't just a hobby, it became a way of thinking that shaped his entire career. Imagine being a teenager who designed a hit game like Theme Park at just 17 years old. For Hassabis, games were more than entertainment. They were complex systems, puzzles that required strategic thinking, creativity, and pattern recognition. And that's the same way he looked at problems in AI and science. In games like chess or Go, you're constantly learning patterns, anticipating moves, and making decisions in uncertain environments. Hassabis realized that if you could teach AI to think like a master gamer, to mimic that kind of intuition and pattern recognition, it could unlock solutions that brute force computing never could. That's how AlphaGo learned to beat the world's best human players at Go, a game where intuition often beats calculation. And it's the same principle behind AlphaFold, where AI was trained to recognize patterns in protein folding that humans had struggled with for decades.
I first came across the problem of protein folding actually as a student at Cambridge in the 90s, because I had a friend who ended up doing his whole career in protein structure, still at the LMB now, would talk about protein folding as the most important problem to crack at any available opportunity, in the bars, playing pool, whatever. This is what he would talk about. So it stuck in my mind as like a really interesting problem. And also even back then, obviously I was doing AI in my games at that point, like Theme Park, and the games that Paul mentioned, but I kind of thought this might be, a good thing for AI at some point. And then the second time I came across protein folding was with the game Fold It, some of you all know about, where I was doing my postdoc at MIT in the late 2000s, 2008, 2009, and I think it just came out, and of course I was fascinated about this idea of citizen science games. I still think there's a lot more actually that could be done there. Like, can you use all of the motivation and time gamers spend on their games? If we could couch our scientific problems in a game, maybe we could kind of harness all of that leisure time to do useful science. So it's a pretty cool idea. And I think Fold It's still one of the best examples of that. And what was intriguing was that the best players, obviously were not biologists, they were just kind of gamers, discovered some real structures. I think for some quite important proteins. I think there were a couple of Nature papers actually published on structures that the Fold It players had found. And what that said to me, and this is a little screenshot of it, is, it was like a puzzle game, right? People bent the backbone and they tried to minimize the energy. And of course, they would sometimes doing counterintuitive moves. So they would make a move that would increase the energy temporarily, and then only for them to do another fold, and then that would reduce it overall. And so if you think about what were these players doing as sort of amateur biologists, well, presumably as they were quite good gamers and they got quite into this game, and they were using their intuition in a way, their pattern matching skills, to figure out what the right moves were. And some of them had got really good at figuring out their intuition for protein structures. So that really then resonated with me when we did AlphaGo, of like, what had we done there? Well, we just mimicked the intuition of these incredible Go masters, right, who spent their entire lives playing Go. Like, you could not find anyone more expert with their pattern matching skills than a Go player.
Demis Hassabis' journey shows us the line between games and groundbreaking science is thinner than we think. By blending creativity, strategy, and cutting-edge technology, he's redefined what's possible, not just for AI, but for all of us. His story is a reminder that sometimes the biggest leaps forward start with a simple question: what if? Thanks for watching. Don't forget to like, subscribe, and explore more stories on innovation with me. Thank you.